So in this lesson, we're going to talk about the precise definition of limit. First of all, let's recall the intuitive definition of limit. In the intuitive definition of limit, we say that suppose f is defined when x is near a. This means f is defined on an open interval contains a, okay? Except possibly at a itself. Then we write the limit as x approaching a, f of x is equal to L. We also say that the limit of f of x as x approaches a is L or equals to L. In this definition of intuitive definition, we say that if we can make the value of f of x, which is the output of the function, arbitrarily close to L, as close as we like, as close as possible. Okay, so let me use as close as possible. So how do we describe as close as possible, right? Question number one, by restricting x, which is the input, to be sufficiently close to a on either side of a, but not to a. Okay, so a may or may not be, defined. Function may or may not define at a. So now this is the precise definition of limit. Okay, so let's take a look. The condition is the same. Let f be a function defined on some open interval that contains the number a, right? It's the same condition. Okay, f function is defined in an open interval near a, right? In the neighborhood of a, except possibly at a itself, okay? Same condition. Then we say that the limit f of x at x approaching a is L, and we write it this way, right? We write it this way, so we have all of that. But here, what distinguishes the precise definition and the intuitive definition is the following sentences. For any epsilon greater than 0, for any positive number, and there is a number delta such that f of x minus L in absolute value is less than epsilon if x minus a is less than delta. What does that mean? What does that mean, right? From the perspective of function, right? So x is the input, f is the function, and the output is f of x. Okay? When in the neighborhood of a, how do we describe, right? We want to make the values of f of x arbitrarily close to L, as close as possible. How do we describe that? We describe that by letting, making the difference between the function and the limit L in absolute value to be less than any epsilon that is chosen, okay? Any epsilon. For any epsilon, so epsilon describes how close the function value is to the limit. And that can be realized because if you have output, you must have input to support those outputs. So those inputs can be identified, and those input is going to be in certain interval. Okay, that interval is in the neighborhood of a. Okay, so as x is approaching a, as x is approaching a, all right, so let me use an arrow, right? And as x is approaching a, how do we describe that? As x approaching a, and that is described by in the neighborhood, right? So this neighborhood, how do we interpret that? How do we interpret that? Now, I'm going to show you the graph just a little later. So let's look at the mathematics. X minus a less than delta, right? Let's first work on this part. Then you say, how about less than zero, greater than zero part? We're going to take care of that part later. This is translated to if and only if. Okay, so this is the same as that x minus a is greater than negative delta, smaller than delta, right? So that's from solving inequalities, absolute value inequality, we get that. And if we add a on all three sides, if we add a on all three sides, we got a minus delta, minus delta less than x less than a plus delta. So that's the interval where those inputs are. So this x, right, to make the output to be as small, to make f of x close as possible, right, which is approaches L. Okay, just allow me to explain this slowly, right? So this approaches L. And how do we describe them? So those axes is described as axis between a minus delta to a plus delta. So in the neighborhood of a. How about greater than zero? So greater than zero really is us to make sure, right? It doesn't matter, right? If for this to be greater than zero, we merely say x may or may not assume the value a. In this case, we don't mind if x is not equals to a. In a lot of the cases, if a is not defined, it's okay. So that's what this condition is for. So this just to say, well, if x is not equals to a is okay. X is not equals to a or x equals to a is not required. Is not required. Okay, so for that's the input. So input is in this neighborhood. Okay, so input is in this neighborhood. What happened to the output, right? The output, it can be as close as possible, right? So that's on input. That's on input and on the output. So let's look at what does that mean on the output? The output is saying, right? Same, is similar for inequality, absolute value. So that means that a negative epsilon is less than f of x minus L. Right, so this quantity, which describes the difference between the function and its limit, and it's between negative epsilon to positive epsilon, and that is the same as saying that in this inequality, if we add L on all three sides, we're gonna get L minus epsilon less than f of x and less than L plus epsilon. So when we say that we want f of x approaches L as close as possible, how close? However close you want, because epsilon is chosen arbitrarily for any epsilon greater than 0. So we want f of x between these two numbers, and that can be guaranteed by restricting. Remember that's by restricting x to be sufficiently close to a. So if x is between these two numbers in the neighborhood of a, okay, I'll draw you then a picture, and the output is going to be inside. So this, any x in this interval will guarantee, if this happens, if this is true, okay, if this is true, then we say the function f of x has a limit L as x approaches a. So now let's interpret what is the interval. That interval is really look like, let's draw a number line. Number line. So this is a minus delta. Right? So this is a, so there's an a here, right? So there's an a here, right? A minus delta, delta is a positive number, so a minus delta, right? So we're gonna put a minus delta right here, right? And over here is a plus delta. So visually you have the interval like that, a plus delta. So a is in the center, a minus delta, a plus delta. So that little interval, okay, so there's a little interval here, a minus delta, right? So a minus delta, comma, a plus delta. So an interval is an open interval. And on this side, it's on the output, right? It's on the output. So the output is that the function is between the interval of L minus epsilon, comma, L plus epsilon. There. Okay. So if this can be guaranteed for any epsilon, there's always such an interval so that the output is going to be in this interval. Graphically, now we're ready for the graph, right? We're ready for the graph. So for any epsilon, we want the function to be close to L, because if L is the limit, the function is to be close to L, as close as you want, as close as possible. So any kind of closeness we wanted is described by epsilon. Epsilon say, okay, I want epsilon to be 0.5, I want epsilon to be 0.01, I want epsilon to be 0.0001. For any one of those requirements, that's for any epsilon. Okay, for any epsilon. All right. For any epsilon greater than 0, so the closeness between the output and the L, right? The closeness of the output of the function to L is described as that. If epsilon is smaller, then this strip is smaller, is narrower. Now, for this requirement, right, L minus epsilon, L plus epsilon, right? And f of x is between that, right? For example, you know, the input, output. So let's just show you the input. Say the input is, say, x, right? So x is here, and its output is right there, right? That's the output, right? And that output falls in the strip. And there's another input, right? There might be another input right here. And its output is going to be right here, right? So all of these output, right? For the first blue output, and this is L, right? This is L. How high is L? This much is L, right? This much is L. So the difference, right? This much is L. So the difference between L and the first function value we just chosen as the example, the difference, I'm going to show you the difference. The difference, I'm going to use orange. Let's see if orange works, right? So between this input and its output with L, the difference is this much. So it's in the strip. And the other one, the difference is this much. So that's the output. We want it to be less than epsilon. You can see both orange color is less than epsilon, right? So you can imagine there are many such orange differences. Many such orange differences which describe for those input, the outputs are it's a difference between the output and the limit is these orange colors. Then the question is, can that be realized? You have a requirement for epsilon. Can that be realized? And the answer is yes. For those inputs, right? So what are those inputs? Those inputs in the neighborhood of A, which is A minus delta. So those little inputs, we have a spot for them. Okay, so those inputs all fall into A minus delta to A plus delta. So here's the input. So here we have a bunch of input. Okay, we use the red. So all the input from this interval, and there's respective outputs, which are blue. So all of these outputs, right? There are many more. Each one, right? There are many input corresponds to many output. All of these output whose difference with L is within this epsilon strip, double epsilon strip. So now, in summary, for those input, x from A minus delta, right? For those inputs, for any required closeness, which is given by epsilon, which you can require any value, then we have input to make it happen, so that all those output corresponding to the input in that interval would be falling within the two double epsilon strip. Okay, so we're going to illustrate this with an example. Okay, we're going to illustrate this with an example. Okay, so that's the, if this can be satisfied, then we say the function has a limit L as X approaches A. So that's the language. That's the language. Okay. Now, for example, take this first example. We have a function, and the function, of course, 2x minus 1. Okay, so the function is 2x minus 1, right? So this is line. And the output, they have many output. In fact, this function is defined everywhere, but we are only concerned that the function has limits in the neighborhood of 3. So A is 3, because we are interested in the behavior of the function 2x minus 1 in the neighborhood of x, in the neighborhood of 3. Obviously, because the function is defined everywhere, it's certainly defined in the neighborhood of 3. Now we want to demonstrate that for any epsilon is greater than 0 compared to the definition, compared to this language. Okay, so I'm going to bring this language over here for your reference. For any epsilon, so here we say for any epsilon, there is a number delta. We have to find that delta. We have to indicate what that delta is. So now then we say, well, for the epsilon you've chosen, I'm going to choose half of epsilon as my delta. And then I'm going to show if x is less than 3, less than delta, which is epsilon divided by 2, right? Then, okay, and then not equals to 3, then I'm going to take my function, subtracting the limit. I'm going to demonstrate to you that f of x minus 5 in absolute value, which I'm following this sentence, right? And then I'm going to plug in 2x minus 1 to substitute f of x, and then we get 2x minus 6. And 2x minus 6, we factored out the 2x minus 3, and we know x minus 3 is going to be less than delta, which is delta is equals epsilon, less than epsilon over 2. So we're going to replace x minus 3 by a larger number, which is epsilon over 2, and we got the difference between f of x minus 5. Absolute value is less than epsilon. So we made this sentence a true statement in our circumstances. Okay, so let me mark these in the same picture, right? So first, let me bring this here. So for any epsilon, okay, for any epsilon, right? So this is a little epsilon. Oh, can't write it, right? So this piece is epsilon, and this other piece is epsilon, right? So we have epsilon, epsilon. So this is double epsilon strip. For that epsilon arbitrarily chosen, and we choose half of that epsilon, which is, we pretend this is half epsilon, this is delta. This from 3 to that piece, that's about delta, and that's about delta. So that's the, let me write it down this way. So this interval, okay, is 3 minus delta, comma, 3 plus delta. That interval. So if we use our arrow to indicate that this end is that piece and that end is this piece. So that's the interval where the input are chosen, their respective output will guarantee, okay, so this piece is L, which is 5. Okay, so I'm going to mark on the, let me move it down over here. That still works, right? So we're going to mark it. This is going to be 5 minus epsilon. 5 minus epsilon. 5 plus epsilon, comma. Okay, so as we mark those points, right? So this piece, that's 5 minus epsilon. And this is 5 plus epsilon. So input, if for any epsilon, you can construct such a picture, you always have an interval in the neighborhood of 3, such that those output will be, the output f of x will be in the neighborhood of 5, in the output neighborhood of 5. If this is true, we have demonstrated it is true, and then we say it is the, f of x has a limit as x approaches 3, which is 5. Okay? All right, so there are a couple of things we like to illustrate from this process. Okay, there are a couple of things we like to illustrate from this process. Number one, we can obviously see delta depends on epsilon. So epsilon, as close as possible, that parameter is arbitrarily chosen. Okay, you can choose any kind of closeness. If I chose epsilon equals epsilon greater than 0, my delta is going to be divided by 2, right? Sorry, divided by 2. Divide by 3 will work too, actually. Divide by 3 will work too. Okay, we're going to show you that later. If epsilon greater than 0, right? So then you say, what are those epsilons are? Examples can be epsilon equals 0.5, then my delta will be half of 0.5. If epsilon is 0.01, my delta will be half of it. So if you chose these delta for the different epsilon, you always have delta. Now you can see delta is dependent on epsilon, which seems to be not quite natural, right? Then you say, well, if delta depends, delta depends on epsilon, how many delta could there be? Node number 3, we say delta is not unique. For example, in our example, I could choose delta equals epsilon divided by 5. Okay. If I chose delta equals epsilon divided by 5, I'm going to work it out. And then I'm going to, this is x minus 3, sorry, this is x minus 3, right? Since x minus 3 is less than delta, right? It's less than delta. And delta is epsilon over 5. And 2 over 5 times delta times epsilon, that's still less than epsilon. You can see delta is not unique. If you find one epsilon, if you find one delta, okay, delta is dependent on epsilon, you will have many, many delta to make it happen. So delta is not unique. Okay, and by this reason, you can choose, for example, you can choose delta equals to third of epsilon. That will also work, right? Okay, so number 1, number 2, number 3, 1, 2, 3. Number 1, you can see the examples of epsilon. This just to show how arbitrary epsilon can be. We use epsilon to describe, we want a function, the output of the function to be as close as possible to the limit. And epsilon is the requirement for the closeness. You want it however close you want. I can always make it happen by restricting X and find the interval of X such that the kind of closeness can be realized. Number 4, how to determine delta from epsilon. And that is an algebraic question. That's an algebraic question. Okay. So I would show you how I decide epsilon is going to be. For any epsilon, I'm going to choose delta equals to half of epsilon, right? And for that matter, I can choose third of epsilon, fourth of epsilon, or a fraction of epsilon. Now I'm going to show you how that is determined. In this case, so since we know what is wanted, right? So we say for any epsilon, oops. Let's see, I'm going to, okay. So for any epsilon, is greater than 0, I want the function to be less than epsilon. Okay, so this is wanted. This is wanted. So I'm basically working backward. I'm working backward. Okay, so if this is true, right? If this is true, then I'm going to take my function and replace f of x, then this will be true, right? And if this is true, I will get, of course, I'm going to put the limit there, 5, right? So simplify this, I'm going to get 2x minus 6. So if this is true, then this is true. Then if this one is true, the next one is true. If 2x minus 6, the absolute value is true, that means that I will have absolute value, 2 times absolute value of x minus 3, that's going to be, that needs to be less than epsilon. Now, you see, we get something for that to be true, for the last inequality to be true, I need to have absolute value of x minus 3 to be less than epsilon over 2. So that's how we decide, okay, let this be the delta. And then when you see the work we've done, right, we work from the final answer to what we want about epsilon, if that can be worked out, okay? And in this case, it's worked out. So you know this process. If you see the proof I have shown you earlier on, you can see it's a reversal. For any epsilon greater than 0, and we're going to show delta is half of epsilon, of course, is positive. If epsilon is positive, half of it is positive. So if I make x minus 3 less than delta, then the function is going to be the difference, between the function and the limit in absolute value is less than epsilon. So that algebra part, okay, is worked from backward forward. All right. So how to show work, right? How do you show work? So let's put note number 5. How to show work? How to show work? When you show work, this part is what you need to show work. Okay. So to prove that, this is the work. This is the work you need to show. If you can show that piece and every step is correct, right? And using the right wording, then you can say thus, right? The limit as x approaching 3, right? We can even write 2x minus 1 is equals to 5, right? So you can put 2x minus 1 here, really. Okay, you can write 2x minus 1 there. You can write 2x minus 1 there. And that's it. So the work you can show to get full credit is this much. Then you say, do I need to show this piece of work? Do you need to show this how part? Right? No, you don't need to show that. You don't need to show that. You can see that these need to stay in the background or scratch paper. Okay, so how to then you work from backward forward, you need to show that on a scratch piece of paper. As you're getting better, you will get better on this. Let's take another example that we have demonstrated. So I'm going to show you the work, right? So here is the work. Prove that this limit x squared times sine x sine 1 over x equals 0, applying precise definition of limits. How do I show work? I'm going to follow. So to show work, we're going to follow the definition. So you basically use the definition. Okay, you use this structure as your guideline, as our guidelines. I'm going to put it right here, right? You can see how I follow that. Really, you just need to show this part. Of course, you need to identify what's delta, right? In this proof, right? And I did some sketch paper work, right? I'm not showing you the sketch paper work. I just want to show the work to get my full credit. So for any epsilon delta, epsilon greater than 0, right? I have the same sentence, and there exists a number delta. So I need to tell the reader I found the delta. And you given me an epsilon greater than 0, my delta is going to be the square root of it. Such that if x is between negative delta to positive delta, which x minus 0, because a is 0 here, then I'm taking this function, subtract the limit of my interest, I take absolute value, and then I need to guarantee from this step to the next step is correct. Okay, so that's what I'm working on. So this piece minus 0, so I can drop the, I have this piece left. And then from this step to the next step, what have I used? I have used, right? So from this step to the next step, I used the reason is that sine of 1 over x, right, is between -1 to +1. It's between that. Or the absolute value of it, right? So the absolute value of it is less than equals to 1. So I used that fact. I substituted the absolute value of 1 over x, right? So let me insert one more step, right? So I have absolute value of x squared on the next step, and also this piece. I take an absolute value separately. So that's allowed. So from this step to the next step is correct. And then on the next step, I drop the absolute value of 1 over x because it is replaced by 1, right? So this is replaced by 1, right? Anything times 1 stay the same. And then the absolute value of x squared is the same as absolute value of x then squared. Well, and we know that absolute value of x minus 0, that's just absolute value of x, right? You could have done, you didn't have to subtract 0. I just put subtract 0 just to show you. So absolute value of x is substituted by a larger number, which is the square root of epsilon. Because absolute value of x is less than delta. So this less than is still be true. And then the square of epsilon is epsilon. So I will guarantee each step is correct. And in the end, right, in the end, do you need to mention this reason? Surely, yeah. But even if you don't mention this reason, most people know this fact, right? Of course, if you mention this reason, it, is add more credit to your work, right? And that is, right? So you would like to add a sentence, i.e., right? So this piece is less than epsilon. And that's it. And this proof is done. This proof is done, okay? Because it follows the same structure of sentences, right? If epsilon greater than 0, we found the delta, and that delta will make, right? For any number you chose, whose absolute value is less than delta, it will make the function subtract its limit in absolute value less than epsilon, which is the desired position, which is arbitrarily chosen. So for this work, you just have to prove this part. All the work you have to show is just this much. Okay? And of course, how do I work it out? Then you can use similar technique to work it out. So by this time, you can see you can have precise definition of left-hand limit. Okay, left-hand limit. Left-hand limit means using the same example that for any epsilon greater than 0, there's a number delta greater than 0 such that this time our x is going to be chosen from the left of 3 in our example here. Okay, but the requirement for the function is still the same. The absolute value of f less than L is less than epsilon. So that's left-hand limit. Okay, if this is true, we say the limits as x approaching A from smaller than A, whoops, it's on the shoulder, smaller than A, and f of x is equal to L. Okay. And the precise definition of right-hand limit, right? It says the A is going to be from the right side of 3, or A, okay? From the right side of the 3, okay? And in this case, we say the limit from, f of x has a limit of L when x is approaching A from larger than, okay, so let me change that to a positive sign. Great. Okay, let me just delete that, redo it. Okay, so right-hand limit. Take an example. Take this one is my example number 3. In this example, we're going to prove the right limit exists, right? So proof. Okay, so we start with if you can start with for any epsilon greater than 0. For any epsilon greater than 0, right? Then I would say there exists delta. How am I going to choose my delta? Right, so I'm going to choose my delta. Of course, delta has something to do with epsilon, right? How am I going to choose that delta? I don't know what to choose yet, okay? So I'm also have my scratch paper, think out aloud. That's my scratch paper. On my scratch paper, I know what the goal I want, okay? So I will want have the function, which is absolute value of x minus the limit, right? I want this to be less than the epsilon, which is chosen arbitrarily. If this is true, right? If this is true, and I also know that x approaching 0 from larger than 0. Why? Because the domain, right? So no, the domain of delta x is x is greater than or equal to 0. We always should be aware of the domain. All right. So if this is what I want, how do I get those delta? So what I'm going to do is that I'm going to take, I can drop the 0 now, right? So absolute value of x, knowing all the x is going to be positive, so I'm going to write it this way. So this has to be less than epsilon. If this is less than epsilon, then if I square both sides, right? If I square both sides, so x has to be less than epsilon squared, isn't it? Epsilon squared. And that's going to be my delta. That's going to be my delta. There you go. We got our delta. So once you get your epsilon, you're going to choose your delta to be epsilon squared. Okay, and then we're going to work this to see, so you can see we're working backward. That's equals to the absolute value of, okay, that, right? And that is equal to, because we are approaching 0 from larger than 0. So we got root x, right? So that's going to be less than the square root, right? So we're gonna let, if, because we got our delta, right? We're gonna have the absolute value of x minus 0, right? Approaching 0, less than delta, less than delta. And because this is approaching 0, so we're gonna get 0 less than delta, right? Approaching 0 from larger. So x is less than delta when I replace x by a smaller number delta, right? X is replaced by a smaller number delta because x is less than delta in absolute value. And this time absolute value is no more needed because we're dealing with positive numbers. And then since the absolute value of delta, and delta is epsilon squared, and the square, and that's going to be epsilon because it's a positive. You don't need the absolute value sign. Okay. Epsilon itself is positive. You don't need the absolute value sign for it. So by this time, we have proved it. We're done. Okay. So let's just say IE, so we can see better. So we have demonstrated that the function subtract its limit is indeed less than. That difference in absolute value is indeed less than epsilon. So you can see for any epsilon greater than 0, for x is between, for x is less than delta, and function minus the limit, absolute value less than epsilon. So we're done. So we have proved, okay, thus finished. So this piece of work don't need to show. That's the work you need to show. That's the work you need to show. Done. Finished. All right. Okay, so next, we have introduced the precise definition of limit, but we also know there's some limit laws, right? We have how many limit laws? Adding, subtracting, multiplying, dividing. We're not going to do all of them because that's going to make this too long. Okay, so hopefully, we're gonna show one. You can work on the others. To prove the limit law by precise definition of limit. So we understand the first limit law is if the individual limit exists, then the limit of sum also exists. So this time we're going to use the definition of limit, the precise definition of limit to prove it. So let's do it. Let's do it. So first, we're going to write proof. Okay, I'm going to put my scratch paper work. Think out aloud. If necessary, I will show you. Okay. What's given? We know that these two limits exist, right? We're going to use them one by one. Since this limit exists, which equals limit number 1, what that means? That means the statement precise definition of limit exists, is true. Okay. What does it mean is true? Right? It means this piece is true. For any epsilon, right? For any epsilon. So if this is true, because we're given it is true, that for any epsilon, there exists a number delta. We call it delta sub 1, right? Such that f of x minus limit sub 1 wait, I think I copied the wrong one. I'm going to use the if absolute value of x minus a less than delta greater than 0. Okay, so we want to use the precise definition. So this is the precise definition of limit for f. So delta sub 1. So this limit exists, meaning this is true. Secondly, for this G, G has a limit too. G has a limit too, right? So we say then this is true, then this statement is also true. But it's for G, right? So I'm going to, so we have another delta for any epsilon delta 2 for G, right? So we just have to change a couple of things. So G has a limit L2, and this is for delta of 2. So now we have 2 delta. For any epsilon, the 2 function has a limit. The 2 deltas may not be the same. May not be the same. Is that okay? Okay, is that okay? Certainly. Okay, certainly. So if for any epsilon greater than 0, there's delta 1, right? How about we say for any epsilon divided by 2, will there be a delta 1? Yes, there will be probably another delta 1, so I can make this to be true. If it's true for any epsilon, it should be true for any epsilon divided by 2. So if we have another delta 1, then you say, how did you change that? Okay, we'll show you that. We'll show you that. All right, so for any epsilon over 2 greater than 0, there's a delta 1 such that this is true. For any epsilon over 2 greater than 0, we're going to have delta 2 greater than 0 such that we got this. But we need to prove this piece has a limit, which is L1 plus L2. What do we do? Okay, so now we have set up this way. We're going to demonstrate, we're going to say that for any epsilon greater than 0, right? And there exists, so how do we choose the delta? There exists delta. We're going to have to choose the delta. So the delta is going to be chosen, okay, to be the minimum, the smaller one, okay, the smaller one, the minimum of the two. Delta 1, delta sub 1, and delta sub 2. Then you say, will that work? Okay, we'll see. Okay, so the delta is chosen, which is the smaller one of delta 1 and delta 2. Okay, such that if, right, if the absolute value of x minus a is less than delta, right here, okay, and greater than 0, okay, and remember delta is less than, this delta is smaller than of the smaller one of these two, okay, so we know this is true. Then the absolute value of f plus g, right? I'm going to take these two functions, subtracting their presumed limit, okay? I can drop the bracket. So this absolute value is, if I'm regrouping it, I'm going to regroup it. I'm going to regroup f of x is going to be regrouping naturally with L sub 1, right? Plus g of x is regrouped with L2 naturally, right? But how are we related? How do we relate these two absolute values? Well, we have something called triangle inequality. Okay, so what does triangle inequality says? Triangle inequality says the absolute value of any two numbers, a plus b, is going to be less than or equal to the absolute value of a plus the absolute value of b. Okay, so this is our a and this is our b. We just regroup them. So into a, b. Even though that parentheses is not necessary, I just want to show you So I can remove it. So next step, we're going to have less than equals to the separate of these two absolute values. So this piece is going to be in absolute value plus, and the other piece in absolute value, which is g minus its limit in absolute value. Right? Now the question is if x minus a is less than delta, right? And certainly, because if x minus a is less than delta, it's certainly less than delta sub 1, because delta is one of the smaller ones. So if it's less than delta, it's guaranteed. It's guaranteed that x minus a is going to be less than delta 1, delta sub 1. And this is going to be true as well. So this is true and this is true because delta is a smaller than one of the two. Okay. All right. So these two would apply, and we already demonstrated that when these are satisfied, less than delta 1, then this is going to be less than. This is going to be less than half of epsilon. Oh, this one half, I'm sorry, this one is also less than half epsilon. Right, so I'm gonna less than half epsilon and plus half epsilon, and that makes epsilon. So i.e., right, f of x plus g of x subtracting the presumed limit is less than epsilon. So now we go back to our narrative of the definitional limit is that for any epsilon, there exists a delta such that f of x plus g of x less than the limit. You know what? I missed a parentheses here. I should have a parentheses here. Okay, otherwise it's going to be a mistake. Okay, so this piece needs a parentheses. All right, so now we have used the definition over and over again. All right, so that proved it. That proved it. So we have done the proof. And now we're going to answer the question. Okay. Thus, this limit law is proved. Now we're going to answer the question, why half epsilon? Why half epsilon, right? Well, once again, we're working. So once again, we know that if this is what we wanted, right? So we worked it out, right? So on the scratch paper, we have done some work. If this is true, right? If this is true, and we know that the this will be true. This will be true. Less than epsilon, right? And if we want that to be true, and from here, we need, if we want this to be less than epsilon, so there's some logic here, okay? So let me explain it to you. So if this is true, right, and that is true, less than epsilon. So if this is less than epsilon, right, we want to finally get this thing less than epsilon, then we have to make this half because they're going to be adding here. So that's why, but that be done, yes. Because if for any epsilon greater than 0, And we can certainly require half epsilon greater than 0, right? Same thing, because they're all both arbitrary. So think out aloud. So we want to, we work this out. So we work this out first on the scratch paper, right? So we decide, okay, we want this to be less than epsilon. So each one has to be less than half epsilon. Then you say make this 2/3, 2/5, and 3/5. Of course you can, right? You can totally change this to be 2/5 of epsilon. This is 3/5 of epsilon, no problem. Or we just keep it. We end up with 2 epsilon, no problem. That still works. Okay, so it's a technique. It's a technical detail that can be worked out and seen in different ways. Okay, so from this point, we decide to make this half epsilon. Or, as we said earlier, there are many such ways to work it out. You can do 2/5 of epsilon, 3/5 of epsilon, or you can just keep your epsilon. You can just keep your epsilon. That's okay as well. That's okay as well, because in the end, you get this difference less than 2 times epsilon. That still proves it, right? So all of these options. But anyway, without further ado, so let's introduce another definition, which is definition of infinite limit. You know, the word infinite limit together always sounds like a little weird, right? Because infinite and limit, they are contradictory. But we do have a proof to show that f of x approaching positive infinity. So here's the definition. So for any positive number m, when we use epsilon, we try to indicate how small it could possibly be. Okay, so in our previous definition, we use epsilon to indicate how small it could possibly be, right? So from the examples we have picked, because we want to get as close as possible. So we use epsilon as a convention. Epsilon is as small as possible. But in the definition of, because it's approaching positive infinity, right? So we also chose a positive number, m, capital M, to indicate how large it can be. But the idea is the same, okay? If there's a number delta such that the value of the function can be as large as possible. So if this is the output, m, right? And you want to be larger than capital M, and M is arbitrarily chosen, and you know, and that can always be done. I can always have an interval. Okay, I can always have an interval. I can always have an interval, right? In the neighborhood of A. So the output can be as high as possible or larger than your M. And this can be done for any M of your choice. This is if this case is true, then we say f of x approaches positive infinity as x approaching A. Okay, so this is the precise definition of positive limit, positive infinity. For example, if we prove, right, so this will be our example number 4. Right? So how do we prove it? Oh, let me clean this up. There's some residual mark. Okay, so proof. How do we prove that? So proof. So we're going to follow the definition for any, right? So we're going to use that sentence structure. For any m, we have to determine the delta here. Okay, so we must determine the delta. So in order to determine the delta, and I'm gonna have a think out aloud to think out aloud. That's my scratch paper. That's my scratch paper. So we want this piece to be larger than M. Okay, length larger than M. Okay. If I want that to be larger than M, if I write it down M over 1, I flip it, then we're going to see X squared is going to be what? It's going to be less than 1 over M, right? Because this is related to the function 1 over X, or 1 over X squared is a increasing function, okay? Is a decreasing function. Decreasing function means what? One input, right? Decreasing function meaning whenever X sub 1, right? X sub 1 is less than X sub 2, right? The function X sub 1 is larger than. So you can see the reverse, right? So f of X sub 2. So that's what decreasing function means. And that's also why we, from greater than, when we flip it, it turned into less than. Okay, so now if we take absolute value on both sides, because it's in the neighborhood of 0, right? So we take absolute value, right? We take absolute value. The left-hand side is going to be absolute value of X, and that's going to be less than, it's going to be less than that. And you can also write it as 1 over square root of capital M. So here we go. So for any capital M larger than 0, our delta is chosen to be 1 over radical M. Okay, so we got our delta, such that if X minus 0, which is absolute value of X, is less than delta, then we're going to demonstrate. Now we need to demonstrate f of X is greater than M. So f of X is 1 over X squared. We don't have this yet. Okay, we have to demonstrate. So from here, right, absolute value of X is less than delta, and 1 over X, we want to show, right? If X is absolute value of X less than delta, what does that mean? It means, right, if we square both sides, whoops, my bad. If we square both sides, okay, this is just algebraic. Okay, if we square both sides, we got that, because this is a given, right? And we flip it. Absolute value of X squared is the same as X squared, because when you square it, right? So now we're going to flip this. We flipped it. Remember, that's a decreasing function. This is going to be turning into greater than delta squared, right? And what is delta squared? Oh, flip it, sorry. This need to be flipped, right? Because we flip this side, we also need to flip this side, 1 over delta squared. And delta squared, delta is 1 over square root of m, so we just have to substitute. So 1 over delta equals to that piece, right? And being squared, this is a pure algebra, and equals to 1 over capital M, and that equals to capital M. So we have demonstrated that for any capital M greater than 0, we found the delta larger than 0 such that the function is larger than the M. So i.e. 1 over x squared, which is a function, is larger than M. Algebraic manipulation, okay? Thus, we have proved that this limit is a positive infinity, right? So we have scratch paper to work with, and the proof part is this much. Okay. Two more definition. Oh, actually, there's more. Okay. F be defined on some open interval. This is approaching negative infinity, right? So, oh no, sorry, not negative infinity. It's left limit approaching infinity. Okay, left limit approaching infinity, and this is the right limit approaching infinity. Okay, so left limit approaching infinity, right limit approaching infinity. And approaching negative infinity. Negative infinity is interesting. So for any n less than 0, there is the number delta such that f of x is less than that, a negative number chosen arbitrarily. Okay. I don't plan to do any examples here because I don't want to make it too long. Thank you for watching.